So in this video, we're going to do ordinary least squared regression in spreadsheets. Now there are many more sophisticated models and software tools out there where you can do regression at the push of a button, and there's a lot more features and functionality. But I want to show you how to do this in the simplest format that can be done in both LibreOffice and in Excel using just functions. So it's a little more work, but it gets to the same result. So the first time I'm going to do this, I'm going to go through by hand. Remember, we found where these two terms, the estimate for the slope term B1 and the estimate for the intercept term B0. And what I'm going to do is use the data that we had, and the only difference here is instead of going from time period 80 to 99, I'm going from time period 1 to 20. I just shifted the time period. All the other data is exactly the same. So what I'm going to do is use this data to calculate my estimated terms for B1 and B0. So first in row 22, I'm taking the average of the Y term and the X terms. And then over here in column C, D, E, and F, you see what I'm doing is I'm calculating each one of these terms. And so column C is just the X, the observed X, minus the average X. Column D is the observed Y minus the average of the Y's. Column E, I'm squaring the X minus the average X terms. And then in column F, I'm just multiplying the X minus the average X times the Y minus the average Y. Why am I doing all these? Because I want to sum them up, because that's what I'm going to be using in my estimate for B1. And then I'll use that in terms for calculating beta naught. All right, let me just clean that up a little bit. So, how do I calculate my B1? Well, I'm simply going to look at the sum of the X minus the Y's, that's column in cell F22, and divide that by the sum of the X minus average X squared. So I just found those two terms, and all I'm doing is punching this back into the equation. The beta naught is going to be pretty simple. It's going to be the average Y's minus the average X's times the trend I just estimated. So at the end of the day, I came up with this equation, which is my regression equation. So my intercept, and this is the intercept at time 0, right? Time 0 here, which is the old time period, would have been time 79, right? Is 113.9, and I still have a 4.14 trend. So if I wanted to estimate the demand at a time in the future, I'd simply plug in that time period here, and that would give me an estimate or a forecast for that demand. Now we could do it by hand, but we want to use a function because we're going to do this with a little bit more. It's a little easier. So we're going to use the LINEEST function, and this is available in both LibreOffice and in Excel. So I've got the same data in column A and in column B. And what I'm going to do in cell D2, I'm going to put this function in, and it's the LINEEST or line estimate, and I've got 4 parameters. The first parameter, which is A2 to A21, is all of the known Y's, and so that's just all of this. The second parameter is all the known X's, and it's just all my X's, my time periods. The third is an indicator of whether I have a constant or not. Always set that to 1. You can estimate these models where you force it to go through 0, but that's generally bad practice. And then the fourth parameter is just another 1, so I want to see all the statistics. So all the known Y's, all the known X's, and then a 1, comma 1. So this is an array function. It's a little tricky, right? Because most functions that we've used so far in Excel and in LibreOffice and any spreadsheet, it returns one value to one cell. What array functions do, regardless of the spreadsheet, is that they can receive and return data to multiple cells. So whenever you have an array function or an array equation, you'll get these little curly brackets on either end of it. It'll be bookended by those brackets when it's active. So the function is the same in both LibreOffice and Excel. Activating it differs slightly. So in LibreOffice, what you do is you go to this cell, here it's cell D2, you enter in this formula, and instead of just hitting return, you hit Control-Shift-Enter if you're in Windows or Linux, and if you're in Mac, it's Command-Shift-Return. Basically the same thing. Just look at your keyboard and see and work that out. And what it will do will populate this cell of 2 columns and 5 rows. It'll populate all those numbers. Now if I'm in Excel, I have to do it a little bit different. First I go to cell D2 and then I highlight and I select a range 2 columns wide by 5 rows deep. In this case you'd go from D2 down here to E6. So you had to have all of these cells highlighted. Then you go up to the insert function area that's usually up here on your spreadsheet where you enter in a function and you type in the linest function. And then once that's in there, instead of hitting return, you hit again Control Shift Enter, or if it's a Mac, Command Shift Return. Regardless of which system you're in, once you do that, you'll get this matrix. And again, you're returning more than just one cell value. It's a whole matrix. And this is a 5-row by 2-column matrix, and we'll explain each of those terms next. So the nice thing about this function, it returns all the information you need. You can have more sophisticated models out there, but they return the exact same information. It just looks a little prettier. But the linest function works very well. So let's talk about it. So I've got this data here, and what I know is, what are my number of observations? Well, I know I have 20, right? We have 20 variables, or 20 observations that we worked with from time period 1 to time period 20. How many explanatory variables do I have? We'll call this K, and we only have 1. The intercept is not an explanatory variable, so it doesn't count. Let me say that again. The intercept is not an explanatory variable. So the explanatory variables are only those things where I'm estimating a slope. So for this, with linear or simple regression, there's only 1. So what I need to calculate is my degrees of freedom. So this will be n, 20, minus 1, minus 1, right? Because k is only 1 here, which is 18, which is given to you right here in my little matrix. So I'm already given that information, and I'll be using that when I do some other calculations. Other information that I'm given is beta naught, right? And remember, that's how we calculate it by hand here. Here it's giving it to me up here in this top right corner. You also get beta 1, and that's up here in the top left corner. And then you get some metrics that give you a goodness of fit. And let me explain that. Let's talk about that a little bit. You need to know how well your model performs. How much is it explaining? How good is the fit? And the way we do this is we look at the sum of the squares. So there's different sum of squares here. I can think of, just looking at the data by itself, there's something called a total sum of squares. And this is where I take each observation and subtract off the average of that, the mean. So all the different daily demand of bagels, I subtract off what the average daily demand is. And for each observation, I square that. That's essentially a good proxy for the variation of the total daily demand. Now I can think of that as being comprised into 2 components when I do a regression model. The first is the amount of that variability that I explain with my regression. Remember, this y hat is what my estimate, that's what I'm estimating. So if I take the sum of the squares of the estimated value for I minus the average and square that, I should be explaining a lot. And then the second component is the unexplained portion, and this is just the yi, the observed, minus what I predicted. This should look very familiar. It's the residual. So the total sum of squares consists of 2 parts. The explained portion, which my regression is doing, that's the sum of square of the regression, added to the sum of the square of the error, the unexplained parts. Now, different texts call these different things. Sometimes this green is called the sum of the squares of the error of the residual. So they're called different things, but at the end of it, it's still just the unexplained portion. And these are given to you in the bottom right and the bottom left cells. And so I could calculate what my total sum of squares is just by adding those 2 together. Now, why do we do all that? Well, we want to come up with this thing called an R squared, which is the coefficient of determination. This is essentially the ratio of what I'm explaining versus the total sum of the squares. And this value, R squared, ranges between 0 and 1. And as I said, it's simply the sum of the squares of the regression divided by the sum of the squares total. And so we give that to you right here in the cell as well. Or you could calculate it. It would just be 11399 divided by the sum of 11399 plus 866. You can check it. It'll come out to be 0.93. So what is it saying? It's saying that this regression is explaining 93% of the total variability in Y in that daily demand. We also get the standard error of the estimate, S sub E, and that's shown right here. And for our model, it's 6.94. And this is the estimate of the variance of the error term around the regression line. And it's simply the sum of the squares of the error divided by those degrees of freedom. And you take a square root of it. It's essentially a standard deviation. We also find the standard errors for each of the coefficients, both the intercept and each of the variables that we have. In this case, it's a simple regression, so we only have one. And so these are found right underneath their estimates. So for B1, it's 0.27. For B0, the intercept, it's 3.22. Why do we need those? Well, it's another test. We want to see if each of the explanatory variables are significant. Are they explaining something? Or are they essentially could just be zero? Are they not explaining anything in our model? How do we test that? We use a null hypothesis that B1 is equal to 0, that the coefficient is 0 and it really has no effect. So our alternate hypothesis is that it does have an effect and that it's not 0. It's either greater than or less than. We're going to test this with a two-tailed t-test, and we're going to use the function tdist that has 3 parameters, and I'll talk about that in a second. And we always use a two-tailed test because we want the alternate hypothesis is whether it's greater than or less than 0. We're not just looking at one-sided, we're looking at both the tails. So we always use the two-tailed test. So we have to calculate the t-statistic, which is simply just the coefficient, the b, over the standard error of that coefficient, SB1. And in this case, for the slope, B1, it's going to be 4.14 divided by 0.27, which are just these numbers from up here. And that gives us 15.33. That's our t-statistic. Now I could go to a statistics textbook, look in the back at the tables, and find out what that does. But we can also use this function tdist. And so this has 3 parameters. The first is that t-statistic, then it's the degrees of freedom, and then the number of tails. Well, we just calculated the t-statistic. That's easy, 15.33. The degrees of freedom, they give that to us, 18. And we always use a two-tailed test. Now this returns the p-value. What's the p-value? Well, the p-value is essentially the probability that we accept the null hypothesis. So what we're interested in is 1 minus that. So we want the lowest p-value. So this comes out, for this case, as 8.92 times 10 to the negative 12, which is tiny, right? So this is much less than 0.01. And so what does this mean? This means we can reject the null hypothesis with 99% probability. Now, I can also use different threshold values. The commonly used ones, even though they're arbitrary, are 0.01, 0.05, or 0.10, which means I can reject the null hypothesis with 99, 95, and 90% probability, respectively. The lower the p-value, the higher the confidence is that that model is explaining something. So how do I go about testing the model overall? Well, let's go back to our original data. And so here's my data in the blue, and I've done my LINEST function, and it's given me my data here. So I look first, see how good is the overall model, the fit of the model. And I look at the R squared. So 0.93, that's pretty good. There's no hard and fast rules of what a good R squared is. Generally closer to 1 is better. For forecasting, usually you need to be north of 70%, 0.7. But these can be anywhere. It depends on the type of thing you're modeling. But that looks pretty good. And then I want to look at the individual variables or the individual coefficients. Are they all explaining something? So I'm going to use the t-test here for each one. And so what I'm doing in cell D9 is I'm calculating the d-statistic, or the t-statistic, for the slope term. And then right beneath that, I plug that right into the tdist function, and it gives me my p-value. And you see for both the intercept In the slope term, it's tiny. It's much less than 0.01. So I can say I'm confident that I can reject the null hypothesis that those variables are explaining something with a 99% probability. So this is a quick overview of how to do simple regression within using a spreadsheet with using just the linest function and the tdist function to test some of the parameters. Next, we'll go in and look at using multiple regression where we can have multiple independent variables.